In a traditional gas-powered car, the act of stopping is inherently wasteful. The kinetic energy generated to get the vehicle moving is simply converted into heat through physical friction. Electric vehicles solve this by using regenerative braking. Instead of relying on friction pads, the car runs its electric motor in reverse. It captures that forward momentum and acts as a generator, funneling energy directly back into the battery. The efficiency gain is significant. An electric motor is typically 85 to 90% efficient at this process, adding 10 to 20% to a vehicle's total driving range just by recapturing energy that used to be lost. Because the brake pedal effectively acts as a charger, drivers often make an intuitive assumption. It feels as though stomping harder on the brakes should force the system to generate a larger, faster spike of recovered power. But telemetry data reveals a counterintuitive reality. Aggressive, hard braking actually reduces an EV's energy efficiency. Getting the most mileage out of a battery requires moving past decades of combustion engine habits and accounting for a specific physical limit built into the braking hardware. The limitation is electrical. The regenerative system is constrained by the strict current voltage capacity of both the electric motor and the battery pack. The battery can only accept a specific volume of kinetic energy, creating a bottleneck. Regardless of momentum, the system can only process a set amount. When a driver makes a hard stop, the deceleration exceeds this threshold, overflowing the battery's intake capacity. To maintain safety, the vehicle's computer automatically activates the backup friction-based disc brakes to slow the car down in time. When those physical brake pads clamp down, the excess energy that could have been stored is instead dispersed into the air as heat. By braking beyond that threshold, the driver forces the EV to behave like a gas car. We see this in the data. A study from Archie-Wu Motorization measured how different foot pressures on the brake pedal directly impacted energy recovery. This chart compares energy recovered at 50 kilometers per hour. Researchers tested a moderate pedal force of 150 newtons against a heavy force of 400 newtons. The results were definitive. The moderate 150 newton force recovered 40% more energy than the heavier pedal application. A study from combustion engines analyzed 60 real-world trips to find the most efficient driving profile. This scatterplot groups the drives into clusters. Cluster C4, marked in orange, showed the highest energy recovery efficiency. These drivers hit the brakes frequently, between 84 and 158 times per trip, but they strictly maintained a moderate maximum braking force. These results confirm that range isn't extended by avoiding the brakes entirely. It's gained through frequent, gentle stops that remain within the motor's processing limit. Staying below that mechanical threshold also has a financial payoff. Relying on the motor for deceleration reduces wear on brake pads and rotors, which can cut maintenance costs for EV owners by up to 50%. The most effective way to stay in this optimal zone is through anticipation. It requires reading traffic lights early and creating more space between vehicles. Lifting off the accelerator earlier gives the regenerative system the distance it needs to absorb energy gradually, ensuring the system isn't overwhelmed by a sudden demand. This is the opposite of the experience in a traditional gas car, where stop-and-go traffic is the worst possible environment for efficiency. By mastering the mechanics of the moderate stop, EV drivers turn a congested city grid from a series of wasteful obstacles into a consistent power source for their battery.